All right, welcome again, everybody, in this virtual meetup. Today, we're going to talk about security tools, the OWASP top 10, and whether or not these tools can cover some or all or none of those vulnerabilities. It says here vendors versus the truth. It implies a bit as, you know, it looks a bit like they were lying. I don't think they're actually actively lying, but when they say they can cover the OWASP top 10, it usually means that they can cover some aspects. And we will have a closer look at what that actually means for a list of common vulnerabilities like the OWASP top 10. Let me introduce myself. First, my name is Thomas Konrad. I'm part of the software security team at SBA Research. SBA Research is a research center for information security based in Vienna, Austria. You know, the country with the woods and forests. And I do software security. Software security has many different phases. Where I came from initially was penetration testing. And I also do some software development myself, where I try to apply what I tell other people and organizations to do in terms of software security, which is harder than I thought initially, honestly. And I also do security training in different aspects of web application security, secure software process. I'm also one of the founders of the Sec4Dev conference and bootcamp, which is a security conference just for software developers. It's not security for security people, but for software developers. And it's going to take place next year in February 25 to 25, 6, 7, 8. So 25 to 28. It's a virtual conference, as you might have guessed already. So save the date if you want to join. So why are we all here? What is our motivation to talk about vulnerabilities and automation? We do software security activities because of different reasons. It might be customer expectations. They expect our software to be secure. It might be expectation of your company, of your boss, of whoever in the company drives security needs. It might be some compliance reasons that you have to fulfill. It also, hopefully there's some sort of intrinsic motivation and engineering principle that you want to write software with high quality. And probably it's a combination of those things. So we have some drivers, internal or external, that makes us want to write secure software. So, but what exactly are the demands? This is often very unclear. People tell you that they want the software to be secure. Now, what does it mean that your software secure? Now, in documents, in references, in guidances, and so on and so forth, you often see lists like the OWASP top 10, for example, that are mentioned. By the way, never ever guarantee anybody that none of the OWASP top 10 is going to be in your software. There probably is one of those in there. It's very, very hard to tell that there's none of those in the software. I want to also look at the new top 10 list. You know, some people would say another top 10 list, one was already more than enough, but I think there are some very interesting aspects that are relevant to APIs in the OWASP API Security top 10. I want to have a look at those as well. So the OWASP top 10, most of you might have heard of those. It's the list of the most common and also most severe vulnerabilities in web applications. It has changed in 2017. So some vulnerability types have left the list, such as, for example, cross-site request forgery was in the list in until 2017, and then it went out of the list because other vulnerability types seemed more relevant. So this is the list of the OWASP top 10. We're going to cover some of these in a little detail, not all of them, but some of these. So in a nutshell, you're going to hear some of those, but this is the list. Now, we also have the OWASP API Security top 10 that have a couple of new aspects. For example, there's one, the API, they are in bold here on the slide, API 3 2019, excessive data exposure. That means, for example, say you have a web application and you have a REST call that fetches your profile data, your name, address, whatever is relevant for the application. And say in that REST API response that carries your profile information, there's a field that carries your password hash as well, or the role that you have in the application. So there's security relevant and sensitive information that is passed to the front end, although the front end itself does not need to know that these fields. That would be an excessive data exposure. Or you can see a list of users because you can send them messages in the application, and you see their password hash in a response if you search for a user. That would be excessive data exposure. Lack of resources and rate limiting is also specific to this list. That means that, for example, you don't have you have a file upload, and you can upload files in that are gigabytes in size, and you have the ability to fill up the disk of that application server. That would be, you have no resources limits set. So that's mostly denial of service related vulnerabilities, but not only. Mass assignment is kind of the opposite side of excessive data exposure. That means, for example, you have a profile update request. So you send a put or patch request to the REST API that updates your profile information, such as an address. And you can add a field that is called role, and you specify a value of admin. And suddenly you're administrator because you overwrote a field that is not supposed to be exposed with this API. That would be mass assignment. I had that exact vulnerability very recently in a penetration test that I just described now. So it's a relevant and a practical thing. Improper assets management means you don't have a list of all your API endpoints and the parameters that are relevant. They just distribute it over source code, and you don't have a fixed list of those things. That's kind of a soft vulnerability. It's not really directly exploitable, but it means you don't know what's there, and it's hard to test. Also, insufficient logging and monitoring means that you, for example, you don't log security relevant information. There is no monitoring that says, for example, if there are 500 access denied responses per minute in your application, that's an unusually high value. There is no monitoring system or anything that creates an alert. Okay. Also, maybe not directly exploitable, but something that's still important for the security of your API. Now, I have merged those two lists because most web applications, for most applications, the OWASP top 10, the classic ones, are relevant, and also the API security top 10, because in modern environments, such as you have a single page application, everything is rendered in your browser, like an Angular, React, or Vue.js framework, and then you have a REST API in the backend. So I merged those two together, and we're going to have a look at which ones of these vulnerabilities can be covered by automation and which ones cannot. We're going to see that later. Now, if you take that list, it looks like a one-dimensional thing. It looks like, there's only one aspect, or they are all equally exploitable, or they all look the same. But that's totally not the case. And that's what I want to shine some light on in more detail. They have different characteristics. They are different in terms of detectability. They are not equally easy to fix, and so on and so forth. Let's have a closer look at what these aspects mean, and I'm going to tell you some examples for each of those aspects. But first, I want to ask you if you find the vulnerability in this code, okay? Say we have an API, a REST API endpoint, where you can fetch your orders, or you can fetch specific orders that you placed in a web shop, okay? I placed the order number 3851. And with this GET request, when I'm logged in as my user account, I can get the relevant details of this order. Now, this would be the control code. And I'm asking you, can you find the vulnerability in this code? Please raise your hand. And we're going to pass speaker rights. Edwin found it. Tell us, Edwin, what's the vulnerability in here? Hi.
I'm not sure if I found it, but I'll try. You should actually check if you are the one that placed the order.
Yes. So you know what that vulnerability is called in the OWASP top 10 or API security top 10?
The rights, no, the, how do you call it? Access. I forgot the English. Basically, the access level is not checked.
Yes, so doesn't matter so much what the name is, but you've spotted this vulnerability correctly. It's called an insecure direct object reference, or a missing object level access control. So you can access objects that are not yours. So that's the point here. If you, for example, you send a post request, or you send a GET request, you send many GET requests in a row, and you take the IDs from 1 to 1000. Probably not all of those orders are yours, but the API is still going to give you all the details of orders of foreign people, okay, that are not You didn't place all those orders. So if you, it looks like an innocent piece of code, but it's not. There's a very, very severe vulnerability in there. So that brings me to the first aspect or vulnerability dimension, if you want, error proneness. If you look at, for example, the question, how likely is it that the developer introduces that error or vulnerability? In that case, very easy, because it's not easy to spot that there is something, there's a weakness in that code. Is there a protection by default by common tech stacks, such as this was Spring code? Not really. I don't know of any mechanisms that automatically protect you against this vulnerability. So no, there's not. So how easy is it to spot the vulnerability? Very hard, I'd say. If you look at the code, it looks innocent and error-free, but it's not. There's a very severe vulnerability in there. So an example for a vulnerability type that has a very high error proneness would be insecure direct object references, the vulnerability that we just saw in that code. The opposite example, or one opposite example, would be Sql Injection, because awareness about this vulnerability is very high. It's been around for a very long time. There's good tooling, there's good framework support. Most frameworks come with some sort of prepared statements by default, and so on and so forth. So error proneness very high with that vulnerability we just saw, low with others such as injection. Low doesn't mean not existent, it means low. Another dimension would be technology support. So how good is the protection by default in common tech stacks? How easy is it to mistakenly bypass those protection mechanisms? If we have a look at the bad example, it would be lack of resources and rate limiting. So if you want to have an upload limit or a limit in how many requests per minute can be made by one user for a specific REST API endpoint, the most frameworks I know, or all of the frameworks that I know, do not have protection by default for this. So there is no automated mechanism to protect you against that. A good example would be XML External Entities. That's a design flaw in the XML standard, if you take it more exactly. With this XML External Entities, you can send a manipulated XML document to a web application that takes XML as an input content type. And then in the doc type header, you have the possibility to kind of define entities, which are kind of variables inside your XML document. And you can point such a variable to a text file on the file system. So with this XXE vulnerability, you can possibly read text-based files from the file system in the name of the application, or you can also denial of service the application. Most XML parsers nowadays have a default value that they don't parse doc type definitions anymore. So in modern environment, you're not going to have this vulnerability. In older environments, you might have it. But technology support and library support to protect against this one is pretty good compared to resources and rate limiting. Automated testability, we're going to have a closer look, even closer look on these testability for each of those vulnerabilities that we saw before. But let me just ask the questions that you should ask if you want to determine whether something is well testable by automated means. How reliable can the tools find this vulnerability? Do the tools also support this specific kind of vulnerability? Just because it's easily detectable doesn't mean the tool actually supports it. Bad testability would be broken authentication. Broken authentication can have very many different aspects. That's kind of a little bit of a catch-all vulnerability class that has many forms of vulnerabilities in there. It's kind of things like you can bypass authentication completely, or you can make brute force attacks, or you can do credential stuffing and all that stuff. Very, very hard to detect by automated means. Whereas, for example, TLS configurations, so cipher suits and cryptographic algorithms, there are good tools out there that can give you a list of what's recommended, what's not, so that we can test that very well. The manual verifiability goes in a different direction. It says if you have a look at the code as a developer, how reliably can it be verified by a human? Now, there are many factors in this. If the protection mechanism is at one spot in the code, you can probably easily verify what's going on. If the protection mechanisms are distributed through the whole code base, it's going to be harder. So how distributed is the information that you need as a developer, as somebody who, as a code reviewer, to determine whether or not we are susceptible to this specific attack. Insufficient logging and monitoring, for example, is something that's that has many different touch points. It has touch points with the application because you have to log security relevant events. Monitoring is probably not inside your application, but you might have a different tool that does analysis on the stuff that is logged. So there are many different things distributed over your tech stack that you need to know in order to verify whether we're protected against this or not. Excessive data exposure and mass assignment. Remember, you can either pass too many arguments to a write request, or you get too many parameters out of a read request. That's something that you can spot pretty easily. Think of, for example, Java Spring, REST API. You have data transfer objects, so you should use data transfer objects for stuff that's passed in and out, and you can easily verify that for a controller action, a DTO is actually in place or not. So that's, you can see that in one single class. You can verify we have a DTO here. Stack distribution, already told you with logging monitoring, stuff is distributed over the whole stack. How heavily distributed are the relevant aspects of the vulnerability over the whole tech stack? Can I see all the relevant bits and pieces from a single perspective? As I already said, logging monitoring is something that is distributed over many aspects of your tech stack. And insecure deserialization, for example, is not so heavily distributed. Insecure deserialization is when you take as an input parameter to your API a natively serialized object, such as, for example, a serialized Java object, and that is deserialized in your application. There are some vulnerabilities that can even lead to remote code execution in some cases, depending on how exactly it's structured. But that's usually, there's one spot where you can see there is a serialized object coming into the application, and that itself already is the vulnerability usually. Also, another dimension is the availability of a defense in depth. So are there good ways to protect to put in a second layer of defense against a specific vulnerability? And can that easily be implemented in my product? For broken authentication, defense in depth is very hard and has many different aspects. It's not really, I can't really tell if there's a defense in depth, that one defense in depth mechanism that protects you against those vulnerabilities. But for cross-scripting, there is a good way of protecting yourself in terms of a second line of defense. It's called content security policy. Content security policy is something, it's a HTTP response header that tells the browser, look, JavaScript code can only be here and there, but not here. And that already is a good defense in depth, because you can specify that your own code is executed, but not the JavaScript code of the attacker that who tries to execute JavaScript in the name of other users. The versatility, so how many different ways are there of this vulnerability? How narrow is the definition of it? And there's also quite an important question, how different are the characteristics that this vulnerability can have in different environments? Look at, for example, security misconfiguration. That's something very environment specific. If you have, I don't know, a scripting language, that might be something different. If you have a compiled language, if you take, I don't know, C# .NET Core project, you can compile it with a debug flag enabled and the production build. Debug flags can have some security implications. That's a security misconfiguration that's specific to this type of languages, not for a scripting language. So it's quite the versatility of this security misconfigurations can be everything, right? So it's very specific to the environment. Using components with known vulnerabilities, this is if you have third-party libraries as a dependency in your code, that's pretty common to all the tech stacks. If you have application, you have libraries in there that have known vulnerabilities. The approach to mitigate this is pretty much the same in all environments. The tooling may be different, but Also, where is the vulnerability best mitigated? Is it something that must be done on the process level, such as, say, known vulnerabilities in libraries? You cannot, you can fix that one library now in code, but there must be a process in place that automatically checks for vulnerabilities regularly. Otherwise, you won't have a sustainable fix for this thing. So this is something that must be fixed in a process level. Is it something that needs to be put in a policy or guide or coding guidelines in order so that developers know how to avoid this vulnerability? Is it a design thing, or is it relevant to the implementation? Are there many such places where I have to mitigate in order to lower the risk, or is it one fix and it's done? So that differs heavily among vulnerability types. Broken function level authorization, for example, can have many different layers where I fix this. And cross-site request forgery might just be, a same-site cookie flag and maybe a CSRF token, and you're done. Now, I want to differentiate between best place of mitigation and best place of assurance. Assurance means even if an error happens, is there some part in my process that catches that error? Okay. So how can I assure that these mitigations are really effective? Is there any test or something that would catch if there's an error? That might be a SAST tool that I have in my pipeline. It might be a DAST tool. That might be a unit test even that I wrote that is checks for specific security functionality, and so on and so forth. So for broken authentication, that's many different things. That's easier tested if you do it in maybe a manual penetration test. If you take, for example, using components with known vulnerabilities, checking your libraries and framework versions for known vulnerabilities, that's usually you have a dependency check and that's it, right? You don't need other assurance bits and pieces in your process. So to sum up this part of the talk, these vulnerabilities are not one-dimensional. They look like a flat list of things, but actually they are not. You can distinguish them in terms of how error-prone they are, how well they are supported in technology nowadays, how well they are testable, and so on and so forth. So they're not let's face this fact that they are not a one-dimensional thing that you can check and you can check the box and you can move on and you're done. It's unfortunately not that easy. We've covered those aspects, but you also got it in your hands. Many of those aspects are not unchangeable. You can design your software in a way that, for example, you can easier verify the correctness of it. Let me give you an example. Say you have an application that has different roles. You have end users that use your web shop, and you have administrators that can administer users and orders and so on and so forth. Now, the verifiability and testability is increased when you have, for example, a URL scheme that already tells me whether this can be called by an admin. Say the URLs start with /admin/, that's admin functionality. Everything else is not. That leads to the fact that I can easily check in my code whether you have the relevant role or not. So I have a centralized piece of code where I check whether this is an admin functionality, and I check whether this currently logged in user has the admin role. Now, the opposite example, a bad example, would be you have distributed your role checks over many, many different parts and abstraction levels within your code. You have a centralized configuration where you check your check your roles roughly. Then you have your controller classes. On some classes, you have it on a controller level. This controller is only admin. Then you have it on a controller action level. This action can also be called by an end user. And then you have maybe something in the template down there. There's another role check because that specific functionality or part of a template can only be called by, or shall only be shown if I'm an admin user, and so on. So if you distribute your role checks over so many different abstraction levels, it's going to be harder to verify and check whether this is true. So on the design level, you have it in your hand. Try to have a good URL scheme that already says a lot about how role checks should be done. And we have it in the hands on some of those aspects to push stuff towards the green boxes to be able to verify things easily. Now, I want to go over some automated tool types. We will cover these four very quickly in a nutshell. Static application security testing, dynamic application security testing, interactive, which is a type of dynamic also, and dependency checks, which is kind of a separate thing that doesn't have a lot to do with the others. Let's start with static application security testing. Now, a static or SAST tool scans the source code. It doesn't have a running application. It doesn't require you to run an instance with test data. It only requires the source code, and it usually compiles a source code if it's a compiled language, or if it's a scripting language, it does not. Of course, it cannot compile. It builds a so-called abstract syntax tree. Looks like this. So it kind of creates an abstract representation of all the ways through your code. Okay. Now, this takes a while for bigger software projects until this AST, or abstract syntax tree, is in memory. And then some rules are applied on that abstract syntax tree. So the general approach of a static application security testing tool is we have some sort of input. That's usually something that comes from the user, such as an HTTP request. You have a way through the source code, and you have a sink. Now, if you have a sink that is potentially susceptible to a vulnerability, such as, say, Sql injection, and you have a user input, so a parameter that comes from an HTTP request, and there is no protection on the way to the sink, then we have a vulnerability. So that's the approach of a SAST tool. We have that input, we have the way through your code, and there might be protection mechanisms or there might not be, and then we have the sink at the end. All right, so abstract syntax tree, there might be an HTTP request somewhere over here, and there might be an SQL statement somewhere down there. And if there's no protection on the way, simply put, okay, that's not really in all detail, but simply put, then we would have a vulnerability. The advantages of SAST are that it has reproducible results, and it has good code coverage, so it can cover all your code. You don't necessarily have to, have test data that makes you reach a certain part of your code. For example, we have test data that has an admin user that also can use this part of the code. That's not relevant for SAST. SAST can see all your code and can see all the ways and paths through your code. A disadvantage is that it only covers your own code. There's also library and framework code that's usually not covered by SAST tools. And it can only detect a limited set of vulnerabilities. Remember that insecure direct object reference, so that the order number that I could iterate, a SAST tool cannot detect this type of vulnerability. It can have some heuristic checks that there is no security check, but it's also very prone to false positives. It lacks context when scanning microservices. Let me explain. So in this modern world of software development, we have services that are small and that are domain specific. In the old world, we had a monolithic architecture. Now, if I throw this source code, you see the red circle on the left. If I throw this source code into a SAST tool, I'm gonna have a good picture of what's going on. We will have some source over here because there might be an HTTP request with a parameter. That parameter goes through the code this way, and then we have a sink over there. And we're probably gonna find a vulnerability if there's, if there's no protection against, let's stick to the example of Sql injection. If there's no protection on the way, we're gonna find that vulnerability. Now, in a microservices architecture, that might look completely different. I cannot scan all microservices at once because the tool is not gonna know where the connection points between those microservices are. It lacks context. So if I throw this microservice here into my SAST tool and I have the source, my HTTP request over there, it goes back to the first microservice, and then the parameter is passed on to the other service. And here we have the sink. Then the SAST tool cannot tell whether there is a vulnerability in there, right? The thing is, in a monolithic architecture, I can see that this is an HTTP request coming from the outside. In the example on the right here, I might also see an HTTP request, but it might come from a trusted source or not. I just don't know. I cannot put this into context. So the new world of microservices is actually something that's bad for the result quality of SAST tools because it lacks context. They cannot tell where stuff is coming from, where stuff is going to. Cool. So the next type will be dynamic application security testing tools. They scan a running application. So they don't have the source code available. They scan running applications, running instances. Some of those tools also have some sort of SAST elements built in for scanning JavaScript code in web applications, but usually they are only DAST. Now, the approach is completely different. It's not source, abstract syntax tree, and sink. It's request and response. So DAST tools send requests to your application. They give the application some input. and they're going to expect a certain response. If a certain response comes back, such as, for example, you see certain patterns or the contents of a certain file or an exception message that says that your SQL syntax is incorrect, something like that. If the tool sees certain responses, it's going to say, okay, here we have an SQL injection or something else. Now, the approach is pretty different. Just one word on interactive application security testing. It's basically a special form of dynamic application security test tools. It's also running application. The difference to DAST is that it has an agent running on in the application. It's instrumented into the application runtime. So you have a DAST tool over there. You have your application here, and there's a little agent running that can see the flow through your code. The advantage is that it can make the results more actionable because it's going to tell you the vulnerability is in here. It's in this source code file and it's on this line. Whereas a classic DAST tool cannot tell because it's only seeing the application from the outside. It doesn't even see the source code in there. And optionally, there can also be a runtime application self-protection. So some IAST tools also have a component in there that automatically protect against vulnerabilities when they detect one. I will, for the sake of simplicity, I'm going to throw DAST and IAST into one pot here for this comparison. The advantage is that they see more parts of your tech stack because they send a request. You know, the request might be going through various microservices, libraries, frameworks, and so on, and they can potentially detect vulnerabilities in all of those because the request goes through the actual running application. It tends to have less false positives because it sees more of the application in terms of, you know, a more complete request and response. Disadvantage is it can only also detect a limited set of vulnerabilities, and single page applications are especially difficult for DAST tools because they need to render the application in a headless browser so that they can then virtually click the button. In classic applications where everything is rendered on the server side, this is easier because the DAST tool sends a GET request to / for example. It gets back an index HTML, and there are links in there. It's easily parsed. You can virtually click that link and send another GET request. For single page applications, it has to load all the JavaScript and then kind of run the application on the client side. OWASP ZAP, for example, has a headless browser built in for automated checks. The thing is, it's quite heavy lifting technologically, so it's quite error prone. Also, a big disadvantage of DAST tools is it's hard to get good code coverage. Let me explain why that is the case. Now, when you do dynamic application security testing, you need so-called known good requests. Let's take as an example a GET API that gets the profile picture when you're logged in, okay, your own profile picture. And we have this thumbnail width parameter over there on the right. It says 200 pixels. So I can specify which width I want to have with the thumbnail. Now, first of all, that parameter might go through input validation. So it might have a look whether it's a number, whether the number is between, say, 100 and 1,000 pixels. It must not be bigger than that. And then there's an if somewhere where it says, is it the original size of the picture or do I have to scale it? And depending on whether I need to scale the picture, I'm going to read it from the file system if it's the original size, and I'm going to ask a scaling microservice that scales the picture down to a certain size. Now, if you do dynamic application security testing, you don't tell the tool which parameter is a parameter that makes sense. You might always be stuck at input validation because if you send an A to that GET request, you're never going to reach all of the microservice down there, for example, right? So you have to feed the DAST tool with known good requests. Now, it might help if you have a front-end application where you can just virtually click all the things and it will generate more known good requests. But if you have just the REST API and maybe a Postman collection or something like that, you might have a hard time because if there are no good default values in the Postman collection or something, you will be hitting input validation all the time. You're never going to get good code coverage. If you're using DAST already, I really ask you measure the code coverage, and you're going to see that it might be surprisingly low. Yeah. So static application security testing versus dynamic testing. As I already mentioned, if you use SAST tools, they scan your custom code, but usually they do not scan your libraries, frameworks, application server, everything that's below the tech stack of your code. DAST tools have the advantage that they also touch everything else in, or most of the other parts of your tech stack, but they usually don't get so much coverage because you might have a hard time coming up with known good requests. So in penetration tests, sometimes we get API documentation, or we get a WSDL file, and they tell us, please do a penetration test. And then the WSDL file is outdated. It doesn't have good default values. We don't know how to compose a request and in which order to call them in order to make calls that actually make sense. And that lowers the test coverage very, very much. And it sometimes takes a long time to explain why we need requests that actually do something. Dependency check is a completely separate category. It scans your libraries for known vulnerabilities, but it only can do so if you have a declarative list of libraries and versions. So if you have, for example, a Java project and you have jar files distributed all over your project and you have committed them to the source code repository, this tool is not going to find anything because it needs a list of this library and that version. It can be a POM XML, or it can be a package JSON in front-end or JavaScript project and so on. But it needs a list that can be read by a machine and parsed by a machine. Okay, that's a very important prerequisite to use such tool. Generally, weaknesses of these tools are that they might know things like injection is bad. So there's probably no case where you want SQL injection in your application, right? But what it cannot know, and I'm talking about DAST and SAST tools here and IAST tools, they cannot know this user must not see that data set. So if there's a missing function level or object level access control in your code, it's not going to reliably detect that because the tool can't know whether you are allowed to make this call or not. How can it know? It can't know. There's nothing to check against. The SAST tool isn't provided with a list of these are the API endpoints and this role can call that and this role cannot. Yeah, there is no list you can check against. So if somebody claims they can reliably detect insecure direct object references and missing function level access control, that's probably not true, at least not reliably. Okay. And also design flaws cannot be detected. So if there's, I don't know, if you don't offer multi-factor authentication, no tool is going to tell you that. That's a design thing, right? You design your application to have a solid authentication. It's not something a DAST or SAST tool can uncover. Now, this is a very, very, very rough list of what can be found by automated test tools. This might not be, or might be true for some types of tools and others not, but that's a very rough estimation, let's call it like that. I'm going to go through some of those examples. So if you look at the first one, injection attacks, they are very well defined. You have an interpreter somewhere that interprets some sort of command. You have a command, and you have user input that can potentially change that command because you use string concatenation between the command and user input. That's the anatomy of an injection attack. That can be easily tested with SAST and DAST tools, right? I would say that these tools are quite reliable with this sort of vulnerability. If you look at broken authentication, however, it's a design thing. It's a design flaw if there's something wrong with your authentication, usually. It has more design aspects than coding aspects. So no, it cannot be detected. TLS configuration, yes, there are tools that can detect this, but it's not SAST, or maybe DAST tools can detect it as well, but SAST cannot. They don't see where your application is deployed. Lack of resources and rate limiting. Again, the SAST and DAST tool is not going to know whether I can call this 100 times per minute or 2,000 times per minute. It doesn't have a list to check against. XML External Entities, something very technical. You have XML document, you have an XML parser that's wrongly configured. If that document goes into the parser, we have the vulnerability. That's easily detectable. Broken object level authorization, not really. I cannot tell whether I'm allowed to call that ID of the object or not. And the tool cannot detect this. There are some tools that they're going to tell you there is no authorization in this method, but that leads to lots of false positives because it's going to report the same thing for all your public APIs as well. So reliable detection, no. Same for function level access control. Insecure deserialization, again, you take a serialized object and you deserialize it. That's quite, you can statically analyze that flow. That works. Number 11, using components with known vulnerabilities. There are tools out there that can check your declarative list of libraries and frameworks against a list of known vulnerabilities. That can be done. But all the other things are quite hard or even close to impossible to be detected by automated means. Now, if you look at that list and you look at the green lines, it's not so many. It's actually quite few that can be reliably detected by automated tools. And all the others, either not really reliable or it depends a lot on the context. So if a vendor claims that they can cover the OWASP top 10, they probably cannot. They can maybe cover specific aspects of each of those vulnerabilities, but they don't. That doesn't mean there is a full coverage of this vulnerability, right? Maybe specific aspects, but even that is really optimistic. I don't think that there's a tool that can cover a single aspect of all of those, right? And that creates a very, very high likelihood of a false sense of security. Be aware that these claims, take a closer look and ask whether this really works for your environment. If they claim something like that, they can cover the whole OWASP top 10. They probably cannot. I want to show you a more sustainable approach. And I'm not going to say that you shouldn't use SAST or DAST tools. I just say use them if you know that they're going to help you. So we said that vulnerabilities have multiple dimensions in terms of how they can be detected, how they can be mitigated, how much they are distributed over your tech stack, and so on. Let's embrace that and let's take this as something granted. What we can do now is, I suggest you to do the following. First, for your software, determine the impact of security incidents. So for example, if the confidentiality of the data is breached, or if the integrity of the data is breached, or if there's a denial of service attack on your application, have a look at what exactly that means for your organization. Is it just public data? So confidentiality might not be a problem. Or is it highly sensitive data of medical systems that it might be a problem? Then document your tech stack, so the frameworks and libraries that you're using. That's important because those libraries might help you for some problems and might not help you for others. Then determine the relevant security vulnerability types for each of those components. I'm going to show you some examples for this afterwards that you can take as a starting point maybe. And then for those relevant vulnerabilities, say cross-site scripting, for example, find out how the technology already helps you, because there might be a mitigation that's on by default in the framework that you're using. Document what still could go wrong. So how could one or developer bypass those protections or forget to, I don't know, or turn it off because they found out that some functionality breaks when it's on. Also document if you have any tests, unit tests, functional tests, integration tests, SAST, DAST, whatever kind of test that might catch an error, okay? Also document if there's a defense in depth in place. And with all those things in place, what risk is left, okay? Maybe you can mitigate, you can push the risk down so far that you can say, we can accept that risk because the residual risk is very low. And document these things as close to your daily work as possible. It's not going to help you if just a document that's on some document server where no one's ever going to look at again. Try to keep this in maybe your source code repository or somewhere close to the tools that you use in your day-to-day work to develop software. I'm going to give you one specific example, or actually 3 examples, but this one we're going to dive in a little bit more deeply. I'm going to have a look at the time. Oh yeah, okay, enough time left. So Angular is a single page application framework that does all the rendering of all the presentation layer in the browser. So all you do is that from your browser to the server, you send small REST calls, maybe back and forth, and you get JSON documents and you render that data in your browser. So you push the presentation layer from the backend into your browser with those single page application frameworks. Now, these introduce a good separation of concerns, and this is usually good for security. So presentation is the responsibility of an application in the browser, and everything else, such as access control, you know, all those things, it's the responsibility of the server. Now, as we have such a good separation of concerns, only a very small set of vulnerabilities is relevant in this type of application, in single-page applications. The same goes for React, Vue.js, and all the others. In short, it's cross-site scripting. So you could place a piece of a string somewhere, for example, in your name or in I don't know, a subject of a message or something like that. And this, you could put some script code in there, JavaScript code. And when somebody else reads that message, the JavaScript code might be executed in their context. So you can attack that person. There are other things, but you know, it's mostly cross-site scripting. How can we screw up? So Angular comes with a very good default protection, but we can bypass security trust. We can configure Angular to render that HTML literally and not encode it and not sanitize it, to be more precise. Or you could entirely bypass the Angular way and say you directly access the DOM APIs instead of using, you know, the Angular templates and all the stuff it gives you already. If you looked at, if you were at the meetup where I showed single page application security concerns, you might remember this part here. There are basically two parts where you can put JavaScript code in Angular templates, that inner HTML. So you can put formatted HTML into that span element that you can see here. So this could be HTML code that also contains JavaScript. Now, the good thing about Angular is it sanitizes it. So if there's any JavaScript code included in that HTML, it's gonna delete that. Okay, so there's no JavaScript code left here at the end, which is a good thing. It's, by the way, the only one of the big three single page application frameworks that do that. The same goes for links. I don't know if you knew that href attributes of anchor elements can contain JavaScript code by specifying JavaScript colon, and there goes your JavaScript code. Now, the good thing about Angular is it sanitizes it by converting JavaScript to unsafe, which probably, you know, it's not gonna make any sense anymore, but you're at least safe from a cross-site scripting attack. Now, if we boil that down to a mitigation tracking list, this is what I want you to do for each vulnerability that's relevant. First, we specify a vulnerability name that's cross-site scripting in a case, and that's pretty much the only vulnerability type that's relevant for Angular. There are, you know, there's regular expression, DOS, and some other things, but that's the most important one. The threat type, so is it confidentiality, integrity, availability, and non-repudiation? It's these three that are concerned by this. I give it a qualitative severity so that I can, you know, prioritize my countermeasures. And I document how does technology help me already. Angular does automatic encoding by default, but there are some ways to bypass that. But the HTML encoding and sanitizing is relevant for the href and for inner HTML. So these are the most two important parts. Edge cases, so this protection is good by default, but I can configure Angular to bypass security trust. That means that this HTML code that goes in here is not sanitized anymore, and it can contain JavaScript code, right? Now, for these edge cases, I might have some automated checks that help me with this. Say, for example, you have a SAST tool in place that disallows bypass security trust, and you have a linter in place. You have a linter anyway when you use Angular in the standard way, and you disallow DOM XSS syncs. There are over 60 DOM APIs that when you pass them a string that comes from an untrusted source, there's JavaScript code in there, it gets executed. So be aware that that's many DOM APIs. And then include a link to those. You can, for example, use the DOM XSS wiki on GitHub, which is a very good source for DOM XSS syncs, for example. Then document whether you have a defense in depth measure in place. It could be a content security policy, which is a very good defense in depth against cross-site scripting. It works best in modern environments. It's very hard to implement in older environments. Now there's some residual risk. For example, we could still use some DOM APIs that are not covered by the linter, and we could still introduce cross-site scripting. But with all those measures in place that I can see in one single document, I can lower the risk to a very acceptable level, probably, right? Now, the important part here is also that we, as these vulnerabilities have so many different touching points with process, with guidelines, with code, with test tools, and so on, take this document as a single or a centralized reference to internal policies, to coding guidelines, to requirements documents where you might have specified that you must protect yourself against cross-site scripting because it's non-repudiation is something we cannot have, right? So this is also a collection of links to all of those things. Another example, Spring and insecure direct object reference, the order example at the beginning. How does technology help? It doesn't really help. There is no standard way to do this. There might be some libraries that can help us do a centralized implementation, but we have a centralized approach for access to objects. Here's the link to that implementation. That might be a link to the source code repository and to that class where this is happening, for example. What are edge cases? This class could not be used, and I could just not use it in my controller. Do we have any automated checks to catch those edge cases? Could be a unit test that checks if random object IDs are used, a unit test that a centralized class is used when the URL has an ID parameter. That's just random ideas. It could be totally different in your software, but that's ideas how you could tackle this. And defense in depth measures, we use random object IDs. A random object ID is a very, very good and effective defense in depth measure against insecure direct object references, because if the access control is missing with that, you remember that GET request where we pass the ID of the order. If that's a very, very long and random ID, say for online attacks, I would suggest at least 64 bits of entropy, then the access control is missing, but I would have to guess a valid ID, which is really hard, right? So it's a very effective defense in depth. I could have, a unit test that checks if all the entity classes actually use random object IDs. That would be very cool. Developers could still bypass all those restrictions, but the residual risk is very low. Again, links to documentation, to the OWASP documentation about this vulnerability, and so on. So this is my source of truth of what I do against this vulnerability. If it's just the knowledge of certain people, and a new person comes to the development team, it's very hard to know what are you doing against it. Is it reliable enough, and so on. So with this, you can say it. Another example, the PHP Symphony Framework. I use this one a lot. And mass assignment. Remember, you can overwrite certain fields in put or patch requests that you are not supposed to be overriding. For example, I'm a non-administrative user, and I can add a role parameter to my put request, and I can make myself an administrator. I had that in a penetration test recently. So what do we do against this? How does technology help? The Symfony form component rejects forms if they contain additional fields. So you're gonna get an HTTP bad request. But I'm not just claiming that. In this document, I include a link to that part of the documentation where it says that, or even maybe the source code file on GitHub where this check is included. Are there any edge cases? Well, I could still use the HTTP parameters and iterate over them dynamically and assign them to entities. So I might have a unit test that checks if HTTP request parameter iteration is used. Okay, so if I iterate over all the parameters, and if that is the case, the check is going to fail and my software is not going to be built. Are there any defense in depth? In this case, there is none. There could still be weird ways to iterate HTTP parameters, but the residual risk is low. Cool. So the advantages of this approach, as opposed to just taking a random float and throwing it at your source code base, is you mitigate what's relevant. It can also serve as a compact coding guideline, because in there you say we don't want to do this because it opens up our application to this vulnerability type. The countermeasures are traceable. So, you know, if you, I don't know, say you have an audit and you have the auditors in your house and they ask you what you do for software security, you can say, look, we have a list of common vulnerabilities. We documented what's relevant for us. We documented what we do about it. Here are the links, and here it is. It's not only for audits, because that's not going to happen every day, but also for your day-to-day work. And, you know, this two-dimensional vulnerability list that we saw at the beginning, you make a 3D picture out of it because you have all those links to different guidelines and to tests and to source pieces of source code and to design and architecture documents and so on. So out of a flat list of vulnerabilities, you make a 3D picture, and you can very quickly see what you're doing for security in your application and software. Cool. So I suggest you to do this for your software. And I want to point out one more thing at the end of this presentation, which is when you approach the security testing, so a new kid on the block of SAST, to be more precise. The problem with classic tools, such as classic static application security test tools or DAST tools, is that they are, as Daniel Cuthbert pointed it out on Twitter, he called them dinosaurs. So they are big, they're clunky, they're slow, they do way too much, they have way too many features, they are way too hard to configure. So they're big, clunky things. That's not really compatible with a modern way of developing software. We want to be agile, we want to be quick, we want to integrate stuff in our security pipeline. We have our CI/CD configured, and we, you know, those things just don't fit in so well with this old concept. I've recently stumbled across this tool. It's called SemGrep. I have yet to test it on my own for my own software, but the first test, and you can do the test in a web browser, looked very promising. So it's a bit like grep. For example, you can grep for a certain function call that happens after another function call, but it's not, it's syntax aware. So if you have in your software, the function call is function name, parentheses, new line, parameters, and new line, parentheses, and you grep for the function call, SemGrep is still going to find it because it's aware that there can be a new line between. It's not just a stupid grep, but it's aware of the syntax of the programming language. It can be easily called on your code, and you can have lightweight means such as there's a Docker container you can use, or you can use this command line tool. And on the website, they have some pre-configured rules. So for example, for Angular, maybe that sounds familiar, you can SemGrep for the use of specific functions. It's not just one-dimensional, so that's not just a grep for a specific function, but you can say, if there's a function call like this, and there's a function call like this over there, and some other stuff happens in the middle or does not happen in the middle. So it's actually real SAST that builds an abstract syntax tree and also can follow the ways through your code. So it's a pretty cool thing. And you can see that the rule syntax is pretty easy. So it's comparatively easy to write your own rules for SemGrep. So that's a new kid on a block that I have no experience with this tool in practice, but I saw this and I thought this is a good approach because it's quick, it's lightweight, it's easily integrated in your pipeline. I suggest that if you want to go that direction, you want to try a SAST tool, start with a couple of simple checks and apply that to your software, and continue adding new vulnerabilities types that are relevant for your software to the list, and maybe some tests with this tool. That's a better approach than just buying a very expensive tool and throwing it at your software and see what you're getting from it. So I'm going to sum up this talk. Key takeaways for today. Vulnerabilities are not one-dimensional. They have very many different aspects in terms of how easily they can be detected, how easily they can be tested, how easy it is to introduce an error, how good technology, framework, and library support is, and so on. So it's not just a flat list and you throw a tool at you're done. That's not as easy. They have many different dimensions. One tool won't do the job. There are tools that have advantages in some areas and others are strong in other areas. So by defining that list of stuff that's relevant for your application, you can get closer to activities that will cover those vulnerabilities. Test tools that will cover them. And when you have that list, you can also, if you evaluate a new tool, you can easily evaluate because you can tell these 3 things are relevant for us. Can you detect those 3? Let us test it, okay? I suggest don't go the approach, develop software, buy a security tool and throw it on the software, but document what's relevant in terms of vulnerabilities and link them to the mitigations, because the mitigations, as we learned, might be best suited on different layers of your development lifecycle. More lightweight tools can be more targeted. They also require more knowledge because you have to understand what's going on in the background, but that's generally a good thing. If you understand the anatomy of a vulnerability, you can easier mitigate the vulnerability. In general, knowledge and awareness about those vulnerabilities and how they work internally is key to a sustainable software security program. I'm on Twitter as well. That's @_Thomas Konrad. If you want to follow me, you can do that. And I'm going to post, software security related stuff mostly and retweet stuff that I find useful on Twitter by other people. And I'm ready to take questions if you have any questions. You can also feel free to raise your hand and to ask your question directly. I'd personally prefer that because then we can actually, talk like humans do. And I love that. But you can also ask it in the questions and answer section. Thomas Kerber asks, hey, thanks for your talk. Some of the modern SAST support their own vulnerability description language, similar to SandGrab, which allows you to fine-tune and extend cases to better fit your tech stack and your architecture. While this sounds like a very flexible and useful feature, I have yet to see a company really embracing this flexibility. Have you seen this used in practice? And if so, how much effort would you estimate is required to fine-tune your SAST using this approach? I have tested many of the, the big players in SAST tools on the market. My personal experience is that the syntax where you define your own rules is very clunky and it's very hard to use. So what you usually do is you use this to whitelist, mostly use it to whitelist stuff that's not relevant, to filter out false positives. This is what you do with those tools. They report too much and you take out what's not relevant. But I don't think this is a very sustainable approach. So I also have yet to see SAST tools that really embrace that mechanism that you define your own rules. Most SAST tools tell you that they know better, and they don't have a very open approach to this. I have seen some syntaxes, but they are really hard to use, in my opinion. Thanks for tuning in. Hope to see you in the next meetup. We don't have the next event planned yet, but we're going to inform you via the meetup platform once we know who's going to be the next speaker. If you're interested in giving a talk at the meetup, or if you know somebody who knows somebody who's a good speaker, please let us know. We're also always looking for good speakers for our meetup. We want the community to be part of this. Thanks for tuning in today and see you next time. Have a nice evening. Bye-bye.